फायर पॉइंट माने जेतोल बर्न करे बुझिले तो
बर्न करी म आरंभ करे सेटा फायर पॉइंट सर
हां हां हां
आगे और सर ऑक्सिलरी सब्सटेंस कोन सर
कोनटा
ऑक्सिलरी सब्सटेंस
ऑक्सिलरी सब्सटेंस कोथिर अछि एटा
एटा अछि से प्रिंसिपल रे जो ग्रीन केमिस्ट्री रो प्रिंसिपल अछि सेफर सॉल्वेंट एंड सब्सटेंस
safer solvent means a solvent auxiliary substance माने auxiliary substance
हां सर so
हाँ
lekha is
auxiliary
sir the use of auxiliary substance that do not directly contribute to structure of reaction product but are still necessary for chemical reaction
means that means some reagents are there some other materials that enhance the rate of the reaction सेगुडा कोइ परिबा हम auxiliary substance
okay sir thank you sir
Okay, so good evening to all of you. Am I audible?
Yes, sir.
Good evening, sir.
Sir.
Okay, where are the other students? They are not joining or what? Only six, only not in six, four. Okay, let us start now. Today we are going to discuss about block 2, the block 2 of your environmental chemistry. In that you have chemistry of air, water and soil. It has three units: air pollution, water pollution, chemistry involving air pollution, chemistry involving water pollution, chemistry involving soil pollution. So now let us start the chemistry, atmospheric chemistry, or the chemistry involving the air pollution, atmospheric chemistry. So what are the components of this unit? So in this atmospheric chemistry, you will discuss about structure of atmosphere, atmospheric stability. In the atmospheric stability, there is atmospheric lapse rate, types of lapse rates and atmospheric stability, importance of understanding atmospheric stability, chemical photochemical reactions of atmosphere, photochemistry of atmosphere, and then distribution of species in atmosphere, ions in the atmosphere, free radicals in the atmosphere, reactions of atmospheric oxygen, reactions of atmospheric ozone, reactions of nitrogen oxide, and then next is particles in the atmosphere, characteristic of particulates, chemical reactions of atmospheric particles, aerosols, black carbon, effect of particulate matter on human health. So these are the components that we are going to discuss in this unit 5. These things we are going to discuss. So basically, what is the importance of atmosphere? You know, atmosphere is anything above our head, and below it's your soil is there and water is there in the soil, and above is the atmosphere where air is there and then oxygen is there that we breathe. Okay, so without oxygen we cannot survive. So to understand atmospheric chemistry is very essential, or atmospheric pollutants is very essential, because when we are breathing oxygen. Along with that, we are also breathing other components of the air, because air has different other components. And if anthropogenic pollution or man-made pollution creates some unwanted chemical species or gaseous species that are harmful to human health. When we are inhaling the atmospheric air, we will also inhale the pollutants, and that will be detrimental to our human health. So that's why atmospheric chemistry is very important to us. So origin of atmosphere, you know, Earth is believed to have formed 4.5 billion years ago from protoplanetary gas dust cloud. Basically, you know, 4.5 billion years ago, our Earth was formed. Hydrogen and helium were the basic gaseous components of the cloud. So no, this is has formed from the protoplanetary gas dust and cloud. Dust particles most likely contain metal and condensates of water, ammonia, methane, mixture of formaldehyde, methyl acetylene. So many organic components, metallic components, water vapors are there. So out of that, our earth has been produced. Okay, so the large amount of gases and vapors possessing high kinetic energy so released got scattered into cosmic space, thus a dense atmosphere so formed. About 3 to 10 to the power 9 years ago, our Earth contained hydrogen, water, ammonia, methane, noble gases, and some sulfur compounds, and as its main component. At the initial state, atmosphere was devoid of oxygen and thus was reducing in nature. So now we have oxygen in our atmosphere, so it is oxidizing. Anything in the presence can be oxidized. Okay, like carbon is oxidized to carbon dioxide, so sulfur is oxidized to sulfur dioxide, nitrogen oxidized to nitrogen dioxide, because oxygen is there. But at that time there was no oxygen, but only hydrogen was there. So that means it was a reducing. Anything in the atmosphere can be reduced. At the same time, a massive condensation of water vapors paved the way for gradual formation of hydrosphere. So condensation of water vapors resulted resulted in the rainfall for a millions of years, continuous rainfall that created hydrosphere. Our seas, our water bodies were created. This phenomenon affected the evolution of the atmosphere by dissolving carbon dioxide in liquid water, which followed the formation of sedimentary rocks. So when carbon dioxide were dissolved, that dissolved and formation of sedimentary rocks started. So on so this is how early universe started. Stage 2, in the second stage of evolution, initiated around 3.5 into 10 to the power 9 years ago, lasted at about 2 into 10 to the power 9 years ago. So for a long period of time, stage 2 continued. Early period was stage 1, when our earth formed. Second stage, when we have hydrosphere is there, water is there, and then slowly sedimentary rocks are forming. So second stage started at that point. During this period, volcanic eruptions resulted in the formation of large quantities of magma saturated with dissolved gases. So what happened is, large quantities of magma means volcanic eruption, because seismic activities. Now the earth is cooler, lot cooler, but earlier the earth was not that cool. The earth was very hot body, and its interior was also very hot. Okay, for that, due to that, there are so many volcanic eruptions were there, occurring all around the earth. So large quantities of magma means the molten substances coming out of the during volcanic eruption. So saturated with dissolved gases. Later, magma moved towards the earth surface of the earth and pushed iron present in the mantle. So atmosphere still typically is reducing the nature due to presence of high concentration of reducing gases like hydrogen, methane, and hydrogen sulfide. So, and was characterized by the absence of free oxygen. So free oxygen was not there. That's why it was still reducing, because hydrogen can reduce a substance, not oxidize. For oxidation process, we need oxygen. Towards the latter era of stage 2, iron moved to the core, and so the ejected gases did not get to interact with iron, and so they were more oxidizing in nature. So gradually what happened is, iron moved to the core, and gradually magma was coming out, and magma gradually pushed the iron to the core of the earth. So these include, so then when then what will happen, then earth becomes oxidizing. What are the oxidizing gases? Like carbon dioxide, sulfur dioxide, water vapors. However, free oxygen was still absent, and the atmosphere continued to be reducing, non-oxidizing in nature. Due to course of time, oxidizing action of atmosphere resulted in the formation of iron oxide, which incorporated into sediments, forming red bed. So basically, then finally oxidation occurs, iron oxide are forming. So that so the next stage is stage 3, where when actually our present atmosphere was formed. So in the third stage, the present atmosphere, oxygen production began to exceed oxygen consumption via photochemical dissociation of water molecules. Okay, so oxygen produced via photochemical dissociation of water molecules. Water molecules in the upper atmosphere absorb ultraviolet radiation and split into hydrogen and oxygen. So oxygen was majorly accumulated in the atmosphere through photosynthesis. So multicellular marine organisms appeared during this period. Then they consumed phytoplankton and floated on the water. With the decrease of phytoplankton, the number of heterotrophic bacteria also declined. So this led to an increase in oxygen in the atmosphere. So then what is the composition? Third stage is the formation of our atmosphere, present atmosphere, where we have oxygen, and gradually life started to begin. Formation of life started to begin. So then we have a bacteria or planktons are there in the water. So we started photosynthesis, and then photosynthesis also produced oxygen. So that's how oxygen balance started, and oxygen formation and maintenance in the atmosphere started. So next, composition of atmosphere. The current atmosphere is a mixture of gases containing nitrogen, 78% of nitrogen, 21% of oxygen, argon about 93%, and carbon dioxide 0.03%, and are the main components. So except for water vapor, whose atmospheric abundance varies from 0.1 to 4%. The proportion of the gas remain nearly uniform below an altitude about 100 kilometers. So basically, there are different gases, water vapors, and other oxygen, nitrogen, argon, and other gases are there. So but major gas is basically oxygen 21% and nitrogen, which is 78%, and carbon dioxide 0.3%, and all other gases those are present are minor quantities. Okay, so the atmospheric gases fall into three categories based on their atmospheric abundance. So major and minor and trace. Major gases, nitrogen, oxygen, constitute about 99% of atmosphere. Nitrogen accumulated over time as a result of its chemical inertness and high molar mass that prevented escape from the region of Earth's gravitation. So gradually, nitrogen is formed, and due to its chemical inertness means they're chemically inert, and high molar mass, they prevented escape from the region of Earth's gravitation. It is believed that denitrifying bacteria in marine sediments serve as the major route for the formation of nitrogen in the atmosphere. Oxygen, almost entirely of biological origin. Oxygen is found entirely of biological origin and is exchanged between atmosphere and the life through the process of photosynthesis and respiration. So generation of origin of oxygen is believed to be from biological origin via photosynthesis and respiration. So you see here in this table the composition of various gases present in our atmosphere has been described. So you see maximum is nitrogen, oxygen, then argon, carbon dioxide, neon, helium, then methane, then krypton and hydrogen. So these are the components of different. So then structure of atmosphere. Atmosphere is classified on various criteria: temperature and chemical species and distance from the earth. Basically, our immediate above our head is the place which is called troposphere. Next to that, stratosphere. Next to that, mesosphere. Next to that, thermosphere. Okay. So then, and also among these four spheres, troposphere, stratosphere, mesosphere, thermosphere, we have different chemical species are there. Not all those, every place we do not have the same composition of air. Air has a different composition in different places, like different spheres. Okay. So distance also, as gradually we go upward, troposphere, then stratosphere, mesosphere, then thermosphere forms. So what is the altitude? Troposphere is 0 to 11 kilometer, stratosphere 11 to 50, mesosphere 50 to 85, thermosphere 85 to 500. So this is the altitude range. And temperature, troposphere is, if you go above 10 kilometers, temperature will cool down to minus 56 degrees centigrade. So temperature of troposphere is in between 15 degree on the ground level to the minus 56 degree, where in the upper atmosphere, where we have the aeroplanes, they pass or go at that point, that is called troposphere, upper atmosphere of the troposphere, where the temperature is minus 56 degree. The next, stratosphere 11 to 50, so its temperature changes from minus 56 to minus 2. Then mesosphere 50 to 85 kilometer, minus 2 to minus 92. And thermosphere, here the temperature gradually increases, so minus 92 to 1200 degrees centigrade. So very high temperature is in the thermosphere, that's why its name is thermosphere. So description of all these have been given here, and what are the different composition of different spheres, troposphere and other spheres. It has been summarized here. So troposphere, you see atmospheric structure is shown here. You see troposphere, stratosphere. At the end of stratosphere, there is a stratopause, and end of troposphere, there is a tropopause, like this. Okay, and then temperature is also varies as you go in a different spheres in a zigzag manner. Okay, so the boundary between the troposphere stratosphere is tropopause, where the lowest temperature is reached. Tropopause marks temperature inversion. Tropopause marks temperature inversion and serves as a barrier, causing water vapor to condense to ice, preventing it from reaching altitude at which it would photodissociate through action of high energy UV radiation. If this happens, hydrogen produced would escape into Earth's atmosphere and get lost. So basically, in upper atmosphere, our water cannot go, and because it's very low temperature at that level, -56, and they get trapped because formation of ice. So ice formation occurs and condensation occurs that prevents the water vapor to go out of the tropospheric range. So gradually water vapor cannot go beyond the tropopause or beyond troposphere. So, and another thing is there is a lapse rate. For lapse, what is lapse rate? In a term called lapse rate is used, which is defined as the rate of change of temperature with altitude. So as we go in the troposphere, gradually the temperature changes with altitude. Altitude means heights. Am I audible to all of you? Okay.
Yes, sir.
So that is called lapse rate. Lapse rate means rate of change of temperature with altitude. For a dry ideal gas, the lapse rate is called adiabatic lapse rate. For a particular dry ideal gas, the lapse rate is called dry adiabatic lapse rate, which is minus 9.8 kilometer per degree Kelvin per kilometer. So that means if you go 1 kilometer above the surface or the troposphere, you will get a lapse rate of change in temperature about minus 9.8 degree Kelvin per kilometer. So that means as you go higher and higher, you will feel cooler and cooler. So that is called adiabatic lapse rate. So next is about stratosphere. In the stratosphere, the main important thing is in stratosphere is about 30 kilometer above our Earth surface. There is a region called ozonosphere. Ozonosphere means a place where about region in which ozone with a concentration range from 10 to 15 ppm. So in ozonosphere, which is in stratosphere, about 20 kilometer above our altitude, above the Earth surface. So that is called ozonosphere, where ozone is there, and it is and its concentration about 10 to 15 parts per million. So it is called ozonosphere. So in that ozonosphere, it has a very good effect on our on absorbing the high UVB radiations or high energy radiations, UV ultraviolet radiation that is coming from the sun. Okay, so basically lambda of those radiations or UV radiations, they range from 190 to 340 nanometer. Basically those are called as UVB radiations, which are very energetic radiations. They, before they reach the Earth, they are filtered at the ozonosphere or stratospheric level by the ozone molecules to before they come to the lower atmosphere or troposphere. So that is extremely important. Then the action or thin layer of ozone is extremely important, acting as a protective shield from toxic effects of UV radiation on living beings on this planet. So basically stratosphere has a ozone layer about 20 kilometer above our Earth surface, and it prevents the passage of harmful UV radiations through it and protects us from the harmful radiations. So what is the reaction that protects us in the ozone layer? So the first thing is ozone formed, and ozone is destroyed by absorption of energy, UV energy. So first thing is oxygen dissociates to two oxygen radicals. Then oxygen radical combines with oxygen molecule to form ozone. So that oxygen ozone by absorbing high energy radiations, it dissociates to ozone and ozone molecule. So oxygen and singlet oxygen radical. So again ozone reacts with ozone oxygen radical to produce two oxygen molecules. So this is how the ozone is formed. That is called Chapman cycle. So the cycle by which ozone is forming is called Chapman cycle. That is also ozone formation layer. That stratosphere is also the zone where ozone is formed. How three oxygens, they combine to form two ozone molecules. 3O2 gives rise to two ozone molecules, and again dissociates back two ozone molecules, dissociate back to three oxygen. The formation and destruction of ozone is a natural process involving absorption of UV radiation and consequent release of heat. It is the heat that reduces the cooling effect and changes the lapse rate from negative to positive. So heat that reduces the cooling effect and changes the lapse rate from negative to positive. So stratosphere represents the boundary. Stratopause represents boundary between stratosphere and mesosphere that depicts upper end of temperature inversion. So basically, you see, temperature inversion means, you see, as you go up in the troposphere, temperature decreases, and after tropopause, temperature increases, and in the again stratosphere, temperature decreases. So then after mesopause, there is again huge increase in temperature. So like this, one layer temperature decrease, other layer temperature increases, again temperature decrease, increase, like this. It continues in different spheres above our surface. So mesosphere is basically from 50 kilometer above the sea level to 85 kilometer. This layer is characterized by the absence of radiation observing species, resulting in decrease in temperature by about minus 92 degrees centigrade with increasing altitude. Apart from that cold temperature, there is very low atmospheric pressure. So at that point, there we have a mesopause, which is extremely cold. Boundary between mesosphere and thermosphere, which is denotes the start of temperature inversion, which again temperature increase. Here temperature decrease. After that, temperature increases. In thermosphere, you see gradually uppermost layer of atmosphere, thermosphere, where artificial satellites orbit the Earth. So this layer is present in altitudes of several hundred kilometers. It consists of minor concentration of oxygen ion O plus and molecular oxygen O2 plus and molecular nitrogen N2 plus, which can effectively absorb UV radiations. Hence, with increasing altitude, temperature as high as 1200 degrees centigrade are observed by the absorption of electromagnetic radiation by the gaseous species. Why this temperature increases? Because there is this gaseous species of nitrogen ion, oxygen ion, or molecular oxygen ions are there. They absorb the electromagnetic radiation or UV radiation from the coming from the sun, and that increases the temperature. So this is how we will study it. And then atmospheric stability. Atmospheric stability means temperature profile of atmosphere in is of utmost importance by determining the stability and hence the degree of mixing of pollutants in various regions and atmosphere as a whole. So that is already I told you, atmospheric lapse rate. The rate of change of temperature of atmosphere with elevation is known as lapse rate, denoted by capital letter gamma. The lapse rate is taken negative when the temperature decreases with altitude, 0 when temperature is constant with altitude, and positive when temperature increases with altitude. So adiabatic lapse rate is then what is adiabatic lapse rate? The rate in which or the rate is that adiabatic lapse rate is that the rate of fall of temperature of rising air adiabatically and involves temperature change due to rising or sinking of air parcel. Basically, you know that when there is a you know why there is a formation of cyclone, how cyclone forms and how cloud are forming in the upper atmosphere, because when we go gradually above the surface, gradually the temperature increases, and then water vapor they condense and gaseous and also even gases also they get warmed up due to sunshine and they go up to the upper layer. When they go to upper layer, they gradually there is a change in the temperature, and that is called air parcel. So air parcel means so air going up due after being hot, getting hotter, and then it cools down in the upper atmosphere. So because of transfer of temperature, so that is called adiabatic lapse rate. So here you see from the if you calculate from the first law of thermodynamics, you can calculate the lapse rate equal to delta T by delta H equal to minus Gm by Cp. Okay, so this is the relationship where by which you can calculate the adiabatic lapse rate. The types of lapse rate should be used to express the rate of temperature change with change in altitude. So there is a two types of lapse rate. One is dry adiabatic lapse rate, other is wet adiabatic lapse rate. Dry adiabatic lapse rate, so basically Earth's atmospheric air is rarely completely dry. Sometimes the humidity is there, so it usually contains some amount of water vapor, and when it contains as much as water vapor, as it is capable of it is referred as saturated air. So basically, when relative humidity is 100%, it is called saturated air. But relative humidity is not always 100%. So then the dry adiabatic lapse rate (DALR) refers to the lapse rate of unsaturated air. That means air with a relative humidity less than 100%. If it is 100%, then it is called saturated air. But unsaturated air with humidity less than 100% is called dry adiabatic lapse rate. If there is no condensation of moisture from air, the cooling effect is about 10 degrees centigrade for 1000 meters of altitude. For example, about 10, there is a decrease of temperature up to 10 degree for 1000 meters or 1 kilometer of altitude. So for Earth's atmosphere, dry adiabatic lapse rate for the about 9.8 degrees centigrade per kilometer, which is almost equal to 10 degrees centigrade per 1000 meters. It depends on the specific heat capacity of air at constant pressure Cp and the acceleration due to gravity g. Owing to the low moisture content, it is mainly associated with stable conditions. So it is called gamma d. So since G and Cp vary little with altitude, the dry adiabatic lapse rate is approximately constant in troposphere. So then what is WALR? DALR with dry, then WALR is wet moist adiabatic lapse rate or wet adiabatic lapse rate. So next is, so basically what is wet adiabatic lapse rate? When there is a sufficient moisture in the air which is rising and water condenses out of it and it releases the latent heat. This type of cooling effect of the expanding air is called moist adiabatic lapse rate, WALR. The moist adiabatic lapse rate is not constant and it varies considerably due to presence of variable amount of water vapor in the air. So what is the WALR, which is the rate of decrease in temperature with respect to altitude varies 4 degrees centigrade in regions where ambient temperature is about 25 degrees centigrade, about 7 degrees centigrade per kilometer in middle or middle of troposphere. On an average, it is taken about WALR is about 6 degrees centigrade per kilometer. As air rises and cools, it may eventually lose its moisture through condensation. The lapse rate then increases and approaches the dry adiabatic value. Wet adiabatic lapse rate is mainly associated with unstable conditions because of higher moisture content. So next is lapse rate and atmospheric stability. So how this lapse rate is basically associated with atmospheric stability. If a atmosphere is stable or not can be determined from this lapse rate. When atmospheric stability may be characterized as very stable, unstable, and neutral. So then, when it is called very stable, a very stable atmosphere is that one has very little that has very little or any vertical mixing of the air. So in very stable atmosphere, the movement of air is very limited. So that's why there is limited mixing, vertical mixing of the air. So a stable atmosphere is the one that inhibits vertical mixing, but doesn't have but does have some motion in the air. Stable means vertical mixing is inhibited, means that means a very less amount of vertical mixing due to air movement of air, but it does have some motion of air. So it does have some motion of the air. An unstable atmosphere is one that encourages continual vertical mixing of the air upwards or downwards. So in all unstable atmosphere is that a continual vertical mixing, either it can go up, the air parcel can go up or can come down due to unstable atmosphere. So that is and that is very essential for mixing of the air. So that means pollutants in the atmosphere can be mixed well if the atmospheric condition is unstable. Okay, if it is stable or very stable, then there is no mixing and there will be pollution build-up. Okay, that's why unstable atmosphere is good for mixing of the pollutants and pollution load will be decreased. And a neutral atmosphere is one that neither discourages nor encourages vertical mixing of the air and is often referred as conditionally stable. So basically, neutral means it doesn't discourages or even encourages vertical mixing of the air, referred as conditionally stable. So first case, tau, gamma greater than gamma d. So gamma which is wet adiabatic lapse rate, or in this case, what is that? Case 1 where the temperature of the atmosphere decreases faster with altitude than the adiabatic lapse rate. So basically that means than the adiabatic lapse rate. Then the atmosphere is turbulent, and in the atmosphere the atmosphere is turbulent and the atmosphere is said to be unstable. So, and it may also be referred as being a super adiabatic atmosphere. So the air from one altitude mixes with the air from other altitude. This feature is responsible for dispersal of pollutants. Vertical mixing becomes desirable. So this is, and from this point, controlling air pollution as pollutants will rapidly be dispersed throughout the atmosphere. So second case, gamma less than gamma d. So that means when the temperature decreases less rapidly with altitude than the adiabatic lapse rate, the air is stable. It may also be referred to as being subadiabatic. Under these conditions, there is very little movement of air from one altitude to another, so pollutants in the air will be restricted. So when gamma is less than gamma d, dry adiabatic lapse rate less than a dry adiabatic lapse rate. So this case, there will be pollution. When then what happens is there is a movement, there is very little movement of the air, and then there will be pollution build up. Okay, so vertical mixing pollutant concentration, without vertical mixing pollutant concentration rises rapidly. Case 3, which is a neutral atmosphere, when that the adiabatic lapse rate, when the actual temperature gradient is same as the adiabatic glass. So this gamma is actual temperature gradient which is equal to the adiabatic lapse rate or dry adiabatic lapse rate. In that case, it is a stable atmosphere. And there is also restriction neutral atmosphere, so that there you have a very limited amount of mixing as well. So basically, temperature inversion, the extreme case occurs when the temperature increases with altitude, resulting in a stable atmosphere. Basically, temperature inversion, the extreme case occurs when the temperature increases with altitude, resulting in a stable atmosphere. So basically, the adiabatic lapse rate thus represents a boundary layer between atmospheric stability and instability. So adiabatic lapse rate represents a boundary between atmospheric stability and atmospheric instability. So adiabatic lapse rate, that's why that term is very important. So the gamma d, which is, so this is adiabatic altitude and temperature, how it varies. Subadiabatic unstable, adiabatic and sub adiabatic is stable. So and then so this is how with altitude, if your temperature varies like this, then it could be adiabatic, it could be inversion, it could be super adiabatic, depending upon how much the temperature varies with altitude. So you see, and then adiabatic lapse rate representing a boundary between atmospheric stability and instability. According to perfect gas law, P equal to rho RT, rho P equal to pressure, rho equal to density, R equal to gas constant, and T equal to absolute temperature. So using this P equal to rho RT equation, you can find out the what you can calculate. You can calculate at the position where TB equal greater than TA, TB less than TA. What is this TB and TA? and then what is an air pressure of pressure air outside the balloon is Ta, and inside the balloon the pressure whatever is there temperature is Tb. Tb is the inside temperature of the balloon, and Ta equal to outside temperature of the air outside the balloon. So if Tb less than for Tb less than Ta, we have rho b greater than rho a. Thus the density of the air inside the balloon is greater than the surrounding air of the balloon, will therefore be pushed to original position. Similarly balloon is lowered from position 1 to 3 1 to position 3, then when Tb greater than Ta, or temperature inside balloon is higher than temperature outside the balloon, that will when the air inside the balloon becomes less dense than the surrounding atmosphere. So depending upon these conditions, whether the balloon can go up or come down, balloon temperature inside or outside temperature varies depending upon that. If Tb get less than Ta and Tb greater than Ta, in that case the balloon will go up or down. Importance of understanding atmospheric stability. The difference between the normal lapse rate and the dry and most moist adiabatic lapse rate determines the vertical stability of atmosphere. So what is the atmospheric stability? So difference between normal lapse rate and dry and moist adiabatic lapse rate determines vertical stability of atmosphere. It also decides the movement of air particles to return to its original position or to accelerate away from its original position once it is given a small vertical displacement. The lapse rate is of importance to meteorologists in forecasting the cloud formation, thunderstorms, and the intensity of atmospheric stability. So next is chemical and photochemical reactions in the atmosphere. So from this atmospheric stability, you know the conditions when the atmosphere there will be a pollution buildup, and the conditions when the pollutants will be well dispersed inside the air. So that's what we discussed. Now we will discuss about the chemical and photochemical reactions in the atmosphere. So what are the chemical reactions that occur? Mostly in atmosphere, majority of the reaction they occur due to photochemical reaction. Photochemical means the energy coming from the sun via either visible light or UV light. They actually help the photochemical reactions. So because they are the energy when they fall on the atmospheric chemicals or whatever gases are there, then there will be some kind of reaction they occur in the atmosphere. So the gaseous atmospheric species can be classified as follows. Inorganic oxides, what are the gases those are present and how we can classify them? Inorganic oxide like carbon monoxide, carbon dioxide, nitrogen dioxide, sulfur dioxide. Oxidants like ozone, reductants like carbon monoxide, sulfur dioxide, hydrogen sulfide, organics like methane, some alkenes and aryl compounds, photochemically active species like nitrogen dioxide, formaldehyde, acids like sulfuric acid, bases, ammonia, and salts are also there. Unstable reactive species like hydroxyl radical, environmentally excited nitrogen dioxide are also there. In addition, both solid and liquid suspended particles play a significant role as source and sink for gas phase species, as sites for surface reactions and a media for aqueous phase reactions. So basically, solid and suspended particles means like there are some soot particles are there, aerosols are there. So they play a significant role as a source and sink for gas phase species. So pollutants can be absorbed or placed over the particles, and then they are also at the surface of those particles. Then also this aqueous phase reaction can occur. So photochemistry of atmosphere. The most significant attribute of atmospheric chemistry is the occurrence of photochemical reaction. So photochemical reaction is what? E equal to h nu. You know, energy is quantized. So energy E of a photon of visible or ultraviolet light is given by E equal to h nu. H is the Planck's constant and nu is the frequency of the light. As a consequence, energy associated with observed photons is sufficient to activate reactant molecules. The transient excited states of the reactant molecules thus formed differ in chemical and physical properties from the original molecules. The chemical species thus formed either transform to new molecules. So basically, the chemical species that formed either transfer to new molecules, combine among themselves or other molecules, or transfer electrons, hydrogen atoms, protons, and or their energy to other molecules. So the photochemical reaction play a crucial role in determining the nature and fate of chemical species in atmosphere. So basically, whatever happening in the atmosphere is determined by this photochemical reaction, the type of photochemical reaction that occur in the atmosphere. Nitrogen dioxide is one of the most photochemically active species present in the polluted air and major contributor to the smog formation. Smog is basically smoke plus fog. If they combine together, that is called smog. On absorption of light energy, or which is E equal to h nu, in the visible or UV region of the electromagnetic spectrum, nitrogen dioxide yields electronically excited molecules. So NO2, when absorb energy H nu, that becomes excited NO2, NO2 star. So then what happens? You see chemistry of air. So basically, you see, when you have particles are there, interchange of chemical species M with particles, electromagnetic radiation is coming from the sun, and then you have M becomes, or by absorption of solar radiation, by the air molecules M, they gets excited, go to M star state, which is excited or energetic reactive species formed upon absorption light. So interchange of molecular species and particles between the atmosphere and the surface, they also occur. So, and due to absorption of energy, they become the molecular species or the gaseous species. They are present in the atmosphere, they get excited. Okay, to goes to excited state. So the nature of excited state may be understood by considering addition of electrons in a molecule. Most molecules contain even number of electrons. The electrons tend to occupy in the orbital with maximum 2 electrons with opposite spin per orbital. So this is how ground state is there. You see opposite spin are there, and in the singlet state, you see two are paired and other two are distributed in other states. So then triplet state, see, two are paired and other two are not paired, triplet state. So that means both. Here singlet state means, see, two are paired, means one state there are two electrons, and other state one electron is there, and the next state is opposite direction with opposite spin. So electron with opposite um, um, opposite spin. But in triplet state, first state where the electrons are opposite spin. Second state where you have electron is only one spin, and then third state the electron is in same spin. So this is how it varies from the different states. For different states, the electron spin varies in the different states. Singlet is the ground state, is where all the electrons are paired. Singlet state unpaired, triplet state are also unpaired. But in singlet and triplet, their spin distribution varies. So you see how oxygen, when you then another molecule is there, and you have a H nu, means like sunlight is coming. So then what happens is, so what happens is, then you have a formation of oxygen molecule, and M, which is higher translation energy. So then dissociation of the excited molecule, O2 star plus H nu becomes O and O. Direct reaction with another species, the energy released during de-excitation is sufficient for the reaction to take place. O2 star plus O3 plus H nu becomes 2O2 plus O. So basically, when the oxygen goes to excited state, it reacts with the another reactive species like ozone to produce two oxygen molecules and a oxygen molecule, singlet oxygen, not a molecule, atomic oxygen. So nascent oxygen, that is called nascent oxygen or atomic oxygen. Then luminescence, loss of energy upon emission of electromagnetic radiation. So that is called luminescence. So NO2 star plus H nu gives you NO2, and then energy is released via the luminescence. This the phenomena of luminescence with instantaneous re-emission of light is known as fluorescence. So the phenomena of luminescence with instantaneous re-emission of light is known as fluorescence. You might have heard about fluorescence. Fluorescence spectrometer we use to study how the light emits when the excited goes to the excited state particular molecule, and when the energy is released, how it occurs. In case if it significantly delayed, fluorescence takes place. Chemiluminescence takes place when there is a formation of excited intermediate which de-excites, releasing some of its energy in the form of light. Ozone plus NO plus H nu becomes NO2 star plus O2. And then energy, intramolecular energy transfer, when energy is transferred from excited species to another species. So the M star is there, then plus Y is there, and H nu is there, M plus Y star. A photosensitized reaction may take place when the second species so generated participates in the chemical transformation. Intermolecular transfer, when wherein energy is transferred within the molecule itself. XY star plus H nu gives you uh, XI star, another XY star, where this cross symbol stands for excited state of the same molecule. Then spontaneous isomerization. Isomerization means, what is isomer? Isomer means same molecular structure, but same molecular weight, but different atomic structure or molecular structure. So that is called isomerization. So if a molecule can isomerize also in the presence of light, sunlight. Photoionization depicts the formation of ionic species with a loss of an electron. So, for example, N2 is excited N2 molecule, nitrogen molecule um, uh, produces N2 plus electron plus H nu. So these are like this. There are so many reactions that can occur via photochemistry or photochemical reaction. So then distribution of species in atmosphere, ions in atmosphere, how different ions are there. So for example, you see so so what is this? This is a basically cross section of Van Allen belt encircling the Earth. So this is what is Van Allen belt. So inner belt and then outer belt. Defense for Earth's uh, um so this is a basically defense mechanism in which there is a the the ions, they do not escape from the ionosphere, as they are strongly bound by Earth's magnetic field. So Earth has a magnetic field. So this magnetic field often protects us from different what high energy radiations that is coming from sun. So one manifestation of this of the influence of Earth's magnetic field on the on these ionizing particles, it's called Van Allen belts. These belts are named after the scientist Dr. James Van Allen, who is credited for this discovery. Van Allen belts consist of a zone of high energy charged particle held by Earth's magnetic field around the planet. If they are visualized as two downwards type shape, if mm, then the axis of the Earth's magnetic field extends through the whole of the downwards, and the belt is divided into another two belts, outer and inner. The outer belt is formed by electrons, while the inner belt consisting of protons is formed as a result of cosmic ray collision in the upper atmosphere. So this is how the ions are distributed over in the atmosphere. So this is basically outer belt is there, inner belt of charged particles are there. So they basically ions, basically they are the ions, and they are hold due to the Earth's magnetic field. And then free radical in atmosphere, atoms or groups of atoms with unpaired electrons are called radicals and are generated in the atmosphere by high energy electromagnetic radiations. Free radicals exhibit high reactivity by virtue of strong pairing tendency of unpaired electrons. They participate in chain reaction wherein one of the products of each reaction is itself a radical. The termination of the chain is marked by the reaction of a radical with another radical. So how this occurs? So you see CH3, there are two radicals, CH3 dot and CH3 dot. They react with each other to produce ethane. So two methyl radicals, they produce ethane. So then hydroxyl and peroxidyl radicals in the atmosphere. So how the water in is there, and then you have they absorb energy to produce hydroxyl radical, that is called free radical. So the production of hydroxyl radical depends on wavelength of light and availability of substrate. Therefore the concentration of hydroxyl radical increases during summer and geographically tropical areas where high humid conditions favor hydroxyl formation. The diurnal plot of the variation of concentration of hydroxyl radical with daytime is shown here. So you see the average diurnal profiles of hydroxyl radical. At what point there is a more amount of hydroxyl radical in the atmosphere, and what time there is no. But it depends upon, as the sunshine increases, then your formation of hydroxyl ion is also increases, because you have more and more energy coming from sun during noon, 12 o'clock, 1 o'clock, 12 o'clock, 2 o'clock. At that time there is a lot of energy that is coming from the sun, and that at that time there will be a lot of hydroxyl ions in the atmosphere. There are so many central role of hydroxyl radical reacts with so many other gases produced or available in the atmosphere. That may be anthropogenic gases or natural gases. For example, sulfur dioxide, it can react. It can react with HX or hollow acids, ammonia, nitrogen dioxide, carbon monoxide, and hydrogen sulfide, nitrogen, to produce different other species. Okay, so that's why hydroxyl radical plays a very central role in the atmospheric chemistry. So sinks for removal of hydroxyl, how which reaction actually control the formation of hydroxyl radical? Like methane, if methane is there, that will basically terminate the hydroxyl radical, and it will form methyl radical and water molecule. Same thing, you go and you can CH3 radical combines with oxygen to produce this methyl peroxide radical. So this is how hydroxyl radical can be controlled or can react with another species, and water molecule will produce. If water is produced, that means the hydroxyl radical is termination. That is the termination of hydroxyl radical. So with this, we saw that how many different type of are there, species are there, and how different type of species are produced, like hydroxyl radical, and they control different photochemical reactions in the atmosphere. So then the reaction of atmospheric oxygen. So oxygen in atmosphere is basically 21% is oxygen. So that too much oxygen is there in the atmosphere. So it's crucial for survival of the life also, oxygen. So methane, basically methane is a natural gas. There it reacts with oxygen molecule to produce carbon dioxide and water. Okay, burning of fossil fuel. What is that? Fossil fuel, during burning of the fossil fuel, basically methane in the natural gas, they burn, and then in the presence of oxygen to produce carbon dioxide. So aerobic organisms rely on atmospheric oxygen for degrading organic matter. So we are inhaling, even small bacteria, they also need oxygen. All living organisms, they need oxygen for their survival. Then oxygen plays a crucial role in chemical weathering. Oxygen reacts with iron to produce iron oxide. So like this, there are so many applications of oxygen. So how oxygen is produced and how it is consumed, and in the ozone layer is also there. In the upper atmosphere, there also oxygen plays a very vital role in formation of ozone layer. So then your photosynthesis is there, respiration, and carbon dioxide is there, generated via respiration, and photosynthesis is also basically takes oxygen, carbon dioxide, and respiration produces carbon dioxide, and then carbon dioxide goes to the water, solubilizes in the water, and forms calcium carbonate. Although it is a very slow process, but carbon dioxide goes and in the dissolved, gets solubilized in water, and it forms reacts with calcium to produce calcium carbonate. So this is how there is a balance of the carbon dioxide molecules and oxygen molecules as well in the atmosphere. Reactions of the atmospheric ozone. So ozone is a vital form of important, very important species in the atmosphere. So how it forms? It forms from oxygen, and also it reacts with oxygen to produce two oxygen molecules breakdown. For its breakdown also it reacts with oxygen. So ozone has it's a protective layer, and ozone, when there is a chlorofluorocarbons are there, chlorinated organics, they actually destroy the ozone layer in the stratosphere, and they contribute to the ozone hole. So when ozone hole is there, so harmful cosmic rays will enter in our earth surface, and we will be all dead because of that. So the ozone layer has a very significant role in protecting our earth from the high energy radiation that is coming from the sun. So next is so this ozone also participate in several reactions. You go through them. Reaction of nitrogen oxides. What are the nitrogen oxide means? Nitrogen, plenty of amount of 78% of the atmosphere is nitrogen. Nitrogen, if produced, that actually reacts with the atmospheric light, or the light energy coming from the sun, and to produce different type of nitrogen monoxide, nitrogen dioxide. So nitrogen oxides are formed from nitrogen via reaction with the light or energy coming from the sun. So there are so many reactions of the nitrogen, how it combustion process, light oxide lightning. So it is a schematic view of principal reactions of nitrogen monoxide, dioxide, and HNO3 in the atmosphere. So how the nitrogen reacts, and formation of different oxides are formed from the nitrogen, and where they go, and how they react with different other species to produce different other reactions. So that is in a cyclic manner it has been described here. So next is another important photochemical smog. There is a photochemical smog is there. That in the photochemical smog, there is a compound called peroxyacetyl nitride, nitric anhydride, PAN. Peroxyacetic nitric anhydride. So this is PAN. So this is a very strong chemical species which is produced from with the reaction with acetaldehyde, which is in the atmosphere, and with hydroxyl ion and different ions, and finally this peroxyacetic nitric anhydride, or PAN, is formed. This PAN is a very toxic gas or toxic chemical species, which is basically creates problem for our different what like different problem, respiratory problem, and when we inhale this type, so there will be respiratory problem or other problems also, and it is a part of photochemical smog. So then next we'll go. I think we have very less time now. 1 hour is gone already gone. So next we will discuss about particles in the gas. Particles already, that what kind of particles are there in the gas? Am I audible to all of you?
Yes, sir.
So slowly you are decreasing. Your number is decreasing. So what are the particles are there in the atmosphere? The atmosphere has aerosol, colloidal size atmospheric particles, condensation aerosol formed by condensation of vapors or reactions of gases, dispersion aerosols formed by grinding of solids, atomization of liquids, or dispersion of dusts, fog, which is a high level of water droplets; haze, decreased visibility due to the presence of particles; mist, they are liquid particles; smoke, particles released by incomplete combustion from fuel. So these are different types of atmospheric particles. And then characteristics of particulates: size. So how can you so the first thing is, to distinguish different type of particulates, we have size. Large particles can be soot or smoke, very small particles like aerosol can only be detected with microscope. Okay, so particle size vary from 2 into 10 to the power minus 4 to 500 micrometer. Particles ranging from 0.001 to 10 micrometer in size are commonly suspended near the source of air pollution. The size of the particle is linked to its potential causing health problems. So basically, if smaller the size of the particulates, it will be more. It will have more health effects, and if the and there could be, it could be lethal. That means it will damage our lungs. But if the size of the particles are higher, so that then there will be no problem, because it will be filtered through our nasal membranes before it goes to our lungs. So basically, if a large particle is there, it is less detrimental than small particles. So there are two types of size ranges: PM 2.5 and PM 10. So PM10 particles have aerodynamic diameter uh, less than or equal to 10 micrometer, and PM2.5 corresponds to particles with aerodynamic diameter less than or equal to 2.5 micrometer. So these two sets of particles differ in their behavior in the atmosphere, and PM2.5 or fine particles tend to remain airborne for a longer period of time and travel longer. So smaller the particles, they remain airborne for a longer period of time and travel large distances. And because their settling velocity will be less, but larger particles, their settling velocity will be higher, and then can be easily come to the ground. So that's why they cannot stay suspended for a longer period. So the PM10, so then concentration, it varies from several hundred per cubic centimeter to 1 lakh per cubic centimeter. So the concentration at any time varies with wind source, because these sources, the sources of release may be very far from site at which the particles are formed. So lifetime, particles lifetime varies from few seconds to several years. Okay, lifetime is it can be, particle can be a short lived or a long lived. Classification of particles: primary particulates, secondary particulates. So we can coarse particulates and fine particulates. So this is how we can compare between primary and secondary particles. Chemical reactions of atmospheric particles: oxidation can be done. You see, oxidation of sulfur dioxide inside the water droplet is shown here. Chemistry of nitrate formation, acid base reaction can be done in the what in when the particulates are there, then acid base reaction can be done. Aerosol, what the next important thing is aerosol. Atmospheric aerosols are what? They are colored and sized solid or liquid particulates of diameter less than 100 micrometer that are suspended in the air and are in equilibrium with the gaseous atmosphere. Particles of aerosol composed of carbonaceous material and oxides of metals, sulfates, nitrates, ammonium salt, and silicon. The composition varies with the particle size. Fine, small particles originating from pollutant like gases like sulfur dioxide are acidic, whereas larger particles that contain materials of mechanical origin, example grinding of limestone, are thus behave like a base. So aerosol could be a basic particle or acidic particle depending upon its composition. So then you see, then black carbon is called soot, also called as soot. Black carbon, a component of particulate matter, is emitted from component of particulate matter is emitted from diesel engines, coal fired power plants, and other sources burning fossil fuels. During incomplete combustion of fuel, carbon dioxide, carbon monoxide, volatile organic compounds, organic carbon, and black carbon particles are formed. Particles of black carbon strongly absorb sunlight and give black color to the soot, which refer to the complex mixture of particulate matter released during incomplete combustion. Basically, black carbon they come out because of the incomplete combustion. If it is incomplete combustion, black carbon will come out. So, effect of particulate matter on human health. Ultra fine atmospheric particles can travel to the respiratory tract, enter to the bloodstream, and release their fatal effects. Short and long term exposure increases the risk of lung cancer, respiratory cardiovascular infection, allergic diseases. PM 2.5 goes to deep inside the body, cause greater damage to the health. Studies have indicated that each 10 microgram per cubic meter increase in the fine particle, fine PM 2.5 long-term exposure has been associated with approximately 6% and 8% increased risk of cardiopulmonary and lung cancer mortality respectively. Other effects include irritation of eyes, nose and throat, several asthma attack, preterm birth and low birth weight, and premature death in the people with heart and lung disease. So I think we are done with the, then this this part, and we will now go to the water chemistry. Water chemistry, in this water chemistry we have distribution of water, chemistry of water, structure and polarity, properties of water, hydrology, physical and chemical properties of fresh water and sea water, physical properties and chemical properties of sea and sea water and fresh water, and their environmental significance. In water quality, the physical water characteristics, chemical characteristics, biological characteristics, and then chemical species in water, organic components in water, inorganic components water. So then distribution of gases in water, oxygen in water, carbon dioxide in water. So these things are there in your water chemistry part. In the water chemistry, importance of water. We need water. About 70% of our human body is made up of water. So that's why water is very essential. Distribution or the quantity and the quality and quantity is available of available water is important factor for well-being of our life. Nearly 71% of the Earth's surface made up of water. So 71% is water. Our sea, they cover about 71%, and only 29% is basically whatever we see, the solid part of the Earth, and liquid covers about 71% of the Earth. That's why a lot of portion is covered with water. But even if we have so much of water is there, out of 97 of the total water is present in ocean. Ocean contains 97% of the total available water, while only 3% is fresh water. Ocean water is highly saline, making it unfit for drinking and agricultural purpose. Out of the remaining 3%, fresh water, out of the remaining 3% is fresh water. 79% is stored in glacier. So out of 97% is gone. That is in ocean, that cannot be used. And 3%, out of the 3%, which is remaining 3% is there, fresh water. Out of that, 79% is stored in glacier as ice, or they are stored in polar region as in the form of ice. 20% is stored in aquifers and soil moisture, and only 1% is surface water. That means only 1% is surface water which is available to us for our drinking purposes. So that's why water is a very scarce commodity. Even though plenty of water is there in the earth, we have only 1% available for our activity. So that's why it is a scarce commodity, and we should use it very carefully, and we should use it in a manner so that we should in a manner that we should not pollute it, protect it from pollution. So properties, physical properties, it's a universal solvent, highest dielectric constant, melting point 0 degree, boiling point 100 degree. So these are the common things already. Maximum density of water is at 4 degree centigrade, higher heat of evaporation, and higher latent heat of fusion, higher heat capacity. All these are the inherent properties of water. And the triple point at about, which is at 0.0060 atmospheric pressure, and temperature is at 0.01 degree centigrade. So at this point, when solid water, liquid water, and the water vapor, they remain in a combined place or together, solid, liquid, and water, vapor, water. They that is called critical point. So next is hydrology. You know the hydrology. Hydrology is the branch of science dealing with study of water on the earth. So hydrology is a branch of science dealing with study of water on earth and beneath the surface of earth. It encompasses the natural distribution and movement of water, the physical and chemical properties of water, and its relationship with the living and material component of the environment. So it is classified into two broad subcategories: limnology, the branch of science that deals with the characteristic of fresh water, including their biological as well as physical and chemical properties; and oceanography, the branch of science dealing with the study of ocean and its physical, chemical, and biological properties. So next is groundwater and water table. Groundwater plays a crucial role in geochemical phenomena such as formation of sediment, secondary mineral. The nature of rock formation strongly influences the quality and mobility of groundwater resources. So groundwater is also there. So you see, if you go down the ground, there is a saturated zone or aquifers are there where your groundwater is stored. Okay, and then you see, but plant has a aeration zone where you have soil moisture is there, aeration zone is there, and um, plant also plays a vital role in transfer of water from the upper layer to the groundwater or the aquifers of the uh, of our to the ground to the aquifers. Okay, where water is stored as groundwater. Sources and uses of water, the hydrological cycle. You know, there is a precipitation, evaporation, condensation, and precipitation. So these three things, they actually termed as hydrological cycle and maintains the balance of water in our earth. So physical and chemical properties of water. Physical properties: the waters of the ocean are different from fresh water in physical as well as chemical properties. The properties of seawater vary with latitude, depth, nearness and to land, and input of fresh water. So basically, its physical properties of water varies. So basically, you see the relative proportions of dissolved salts in seawater. So you see 55% is basically chlorine is there, chlorine. So then 30% is sodium is there. Apart from that, sulfate, magnesium is there, calcium, potassium. So these other minor salts are there. This is the basically the composition of your salt water or seawater. Chemical properties: amphoteric nature. Water is amphoteric and can act as a acid and base. For water, when reacts with ammonia, hydronium ion forms, and water when reacts with hydrogen sulfide, hydronium ion also forms. So basically, it's amphoteric. It behaves as both acid and base. Next, hydrolysis reaction. Since water has high dielectric constant, it has a very strong hydrating tendency. It dissolves many ionic and polar compounds easily. Some more reactions occur in seawater. Total concentration of carbon dioxide is very high in seawater in comparison to atmosphere. So, lot of amount of carbon dioxide also dissolved in seawater. So that forms carbonic acid, and from carbonic or bicarbonates or carbonate ions, about 90% of the total organic carbon is converted to bicarbonate. During the conversion of carbon dioxide to bicarbonate and carbonate, hydrogen ions are also liberated. However, the relative high concentration of both total inorganic carbon and boron in seawater are sufficient to maintain pH of seawater between 7.4 to 8.3. So thus, buffering of the amount of hydrogen ion is liberated. Basically, always the presence of this carbonate, inorganic carbon, and boron in the form of dihydroxyboron or tetrahydroxyboron. So they actually maintain the pH of the water. Saline. So what is the comparison between physical properties of fresh water and seawater? Fresh water has salinity is very less. Seawater salinity is more. Dissolved ions are very less in fresh water, whereas seawater is very high. Electrical conductivity of fresh water is low. Marine, due to the presence of lot of salts, electrical conductivity of the seawater is high. pH of the fresh water is neutral. Salt water is more basic because they have higher salt content. Density, fresh water has less density due to dissolved salts. Marine water is denser. So then freezing point. Freezing point of fresh water is 0 degree centigrade. Seawater freezes at a temperature lower than fresh water. The freezing temperature varies with the salt concentration. More is the salt, lower is the initial freezing temperature. Dissolved oxygen. Dissolved oxygen of fresh water is more easily than oxygen dissolves in fresh water more easily than salt water. Because of that, salt water has less dissolved oxygen than the fresh water. Fresh water means what? Water found in river, ponds, all those are fresh water. Salt water is found in mostly in sea. Temperature fluctuations, tonicity, so all these are different parameters. They vary for seawater and freshwater. So next, environmental significance. A freshwater ecosystem comprises of stream, wetland, ponds, lake, and rivers. Freshwater, what is a freshwater ecosystem? That comprises of wetlands, streams, ponds, lakes, and rivers. Whereas marine ecosystem, that is basically marine, means like sea. Coagulation and sedimentation. What is coagulation? The most commonly employed methods in water treatment are called coagulation, flocculation, sedimentation, filtration, and disinfection. So these are the four methods to treat water: coagulation and flocculation, sedimentation, and filtration. Coagulation of colloidal particles is important to understand the number of processes like industrial processes and aquatic chemical phenomena. The colloidal particles in mineral aggregates and separate from water is significant in the formation of mineral deposits. Aggregation of particles is a complex phenomena and may be divided into two categories: coagulation and flocculation. So when the aggregation of colloidal particle, when they combine together, their size becomes bigger. When the size becomes bigger, they can easily settle down. So they can settle down, like pollutants are there, water pollutants. You add a coagulant that helps in coagulants, or coagulant means that help in formation of larger particles. So then of the pollutant molecules, and when the particles becomes larger, they will gradually settle down because their settling velocity will increase, and they, with the gravitational force of the our earth, they will settle down. So that's how we can separate the pollutants by coagulation process. Basically, coagulation means when you add a colloidal particle, they tend to coagulate, and coagulate means join together and make bigger particles, and then they gradually settle down. That is called coagulation. There are many coagulants are there. What are the coagulants? They are added like aluminum sulfate, polyaluminum chloride, and then ferric sulfate. They are used as coagulants. Filter alum Al2SO4 18H2O when added to the wastewater. The hydrated aluminum ion, which is acidic in nature, reacts with base to form gelatinous precipitate of aluminum hydroxide that carries suspended matter with it as it settles. Thus, the alkalinity of water is also reduced. Flocculation. Flocculation is the process. In some cases, colloidal particles are allowed to settle in the presence of bridging compounds that interact with colloidal particles through chemical bonds. Join them via bridges and induce coagulation called flocculants. So this process is flocculation. Flocculation is similar to coagulation, basically making bigger particles to settle down. So natural and synthetic polyelectrolytes are used as flocculants. Next is sedimentation. Wastewater can be treated by several physical processes. For example, solids can be removed by sedimentation and filtration. Sedimentation involves physical pre-treatment of water before application of other purification treatment such as filtration and disinfection. It may be defined as the tendency of the suspended solids in the suspension of water to settle out the suspension under the influence of gravity. So that is called sedimentation. When the coagulants or flocculants are formed, the larger particles, they will settle down in the influence of gravity. So gravity has tendency to pull everything towards itself. Then water quality. What are the parameters? There are three types of parameters of water. Physical characteristics like temperature, color, odor, turbidity, and solids. Chemical characteristics like pH, conductivity, salinity, hardness, and BOD. And the biological characteristics, they are basically how many types of organisms or group of organisms they are present in the water. So that is called biological characteristics. So physical characteristics: temperature, color, taste, odor, turbidity, solids. Total suspended, total dissolved solids or suspended solids. Next is chemical characteristics like your pH. You know already in pH is basically neutral. pH means around 7. If it is higher than 7, it is basic. If it is less than 7, it is acidic. Am I audible to all of you?
Yes, sir.
So these are the chemical characteristics. Then next is electrical conductivity, salinity. Salinity means how much amount of salt content is there. Alkalinity, the capacity of water to accept proton, H plus ion, is called alkalinity. Alkalinity plays an important role in water treatment, chemistry and biology of neutral water. Acidity, it is defined as ability of water to neutralize the hydroxyl ion. The presence of weak acids such as phosphates, carbon dioxide, hydrogen sulfide, proteins, fatty acids, and acidic metal ions, particularly iron 3 plus, are responsible for acidic character of the water body. Polluted water contains as an appreciable concentration of free mineral acid. The term free mineral acid refer to strong acids such as strong acids such as sulfuric acid and hydrochloric acid in water. Next is hardness. Hardness of water is essentially due to presence of calcium and magnesium minerals present present naturally in water. A common manifestation of hard water supply includes poor lathering of soap and scum accompanied by formation of cloudy precipitate. So basically, there will be white precipitate will form when you boil the water. So that is due to hardness or presence of calcium and magnesium salts. Okay, so basically when you use that hard water for cooking purpose, your dal will not be cooked, your rice will not be cooked properly. And if you use that for washing, your soap or detergent, effect of the detergent will be nullified because of the presence of calcium and magnesium salt, the hardness. Okay, so that is the drawback of this hard water. There is a temporary hardness and there is a permanent hardness. Temporary hardness is due to the presence of bicarbonate of calcium and magnesium in water. Permanent hardness arises due to presence of sulfates and chlorides of calcium and magnesium. Basically, carbonate and bicarbonate is there, that is called temporary hardness. If the chlorides and sulfates are there, magnesium of the calcium salts, they are called permanent hardness. Okay, so then biochemical oxygen demand. It is the amount of dissolved oxygen required to degrade the organic matter from water by aerobic organisms at a given temperature over a specific period of time. It widely used as an indication of the organic quality of water and thus indicates the pollution level. It is expressed in milligrams of oxygen consumed per liter of sample during 5 days. So it could be BOD 5. That means it is milligrams of oxygen consumed per liter of sample during 5 days of incubation at 20 degree. When organic matter decomposes, microorganisms feed and organize the decaying material. Greater is the action of microbes, the more oxygen will be used of giving a high measure of BOD, leaving less oxygen for aquatic life. So basically, if pollutants are there, it will take away the dissolved oxygen present in the water, and there will be less and less amount of oxygen available for the aquatic organisms, and that will lead to their death. So death of the aquatic organisms like your fish will occur because these oxygens, dissolved oxygen in water, will be used for oxidation of the pollutants present in the water. So that is, so then biological characteristics. Microorganisms like bacteria, fungi, protozoa, and algae are naturally present in the water and act as living catalysts, playing as a significant role in vast number of chemical processes in water and soil. So these microorganisms like bacteria, like cholera bacteria, it's a waterborne disease. Cholera is a waterborne disease. It go if you take contaminated water, it will you will fall in the cholera disease or dysentery. There are many waterborne diseases are there. So when the virus or the bacteria, they pass through the water to human bodies. So that is called that is called basically waterborne diseases. So next is chemical species in water. What are the chemical species they are present in water? Organic component in the water. What are the, because of human activity, many organic components they come into the water, like soap. Soap is a basically long chain, basically sodium stearate. It's a ester, sodium salt of ester. So that is, they are produced by soaps are produced by saponification, and then we use it as a cleaner because their ability to act as a emulsifying agent, lowering the surface tension of water. Okay, emulsify, and then the organic part of the soap is a ionic carboxyl head. Its hydrophilic nature allows soap to interact with water molecules via ion dipole interaction and hydrogen bonding. So the hydrophobic part of the soap is a long non-polar hydrocarbon chain. Soap has a two. One is hydrophilic. This part, the top part, this carboxylic part. So this part is hydrophilic, and this long chain is hydrophobic. So how the soap forms the micellar structure. Micellar means a globular structure. Then detergents. Unlike soaps, synthetic detergents are excellent cleaners, and they neither form insoluble salts with hard water nor wash out of acidic water. A molecule of detergent consists of two major components, surfactant and builder. Surfactant makes water wetter by lowering its surface tension, owing to the amphiphilic structural attribute consisting of both hydrophilic groups and an acidic anion. So this is basically, detergent is a better than soap for cleaning. So these are the components of detergents. Okay. So they are called alkyl benzene sulfonate, ABS. Next is insecticides. We use for agricultural purpose. Insecticide, pesticides we use for agricultural activities and to killing insects. Okay, for household activities also. So they go by the when you are washing our home, or they pass from our home to the water bodies. So insecticide is a part of the water nowadays. Okay. So chlorinated hydrocarbon, what are those type of? DDT, methoxychlor, dialdrine, aldrine. So there are so many, heptachlor. So there are many chlorinated organics. They are used as what? Pesticides or insecticides. Then organophosphates, they are also very strong chemicals. They can kill them. So some organophosphates like in insecticides are also there. Although some organophosphorus compounds are highly toxic to humans, they are biodegradable and usually break down in environment and do not accumulate. So this is, then carbamates. Organic derivatives of carbamic acid are known as carbamates. This group of insecticides include carbaryl, carbofuran, and so carbamate are also the carbamates. So then herbicide. Herbicide means to kill herbs, weeds, unwanted plants without affecting the main crop. Initially, inorganic compounds like sodium arsenate, sodium chlorate, copper sulfates were used. However, owing to their toxic and non-biodegradable behavior, they are replaced by organic compounds like heterocyclic compounds like atrazine, metribuzin. So these are the herbicides. Substituted amide derivatives like propanil, achlor, bipyridinium compounds like this. So next is chlorophenoxy compounds. This family of compounds include 2,4-dichlorophenoxyacetic acid, 2,4-D. Okay, so and 2,4-trichlorophenoxyacetic acid 2,4,5-T are used for weight and brush control. They are even employed as military defoliants. So this, so then polychlorinated biphenyls, so they are also there. So these are some organic compounds, they are found in water. Oil, inorganic components, these are organic components. Then inorganic components, metal ions, trace elements, and then lead, mercury, heavy metals are there, and then beryllium, boron, chromium, copper, fluorine, iodine, iron, molybdenum, manganese, selenium, zinc, lead, mercury, cadmium. These are some inorganic components. So I already told you last class also, cadmium, lead, they have very detrimental effect. Mercury is also very detrimental effect. Okay, cadmium is ita disease due to cadmium. Mercury has a lot of very detrimental effects are there on kidney, liver, and human health. Arsenic is also a very important pollutant, and it can kill human beings if if consumed in more amounts. Acute poisoning results from the ingestion of more than about 100 milligram of arsenic, while chronic exposure can cause arsenosis, including skin lesions, black foot disease, peripheral vascular disease, and cancer. Like mercury, bacterial action also convert inorganic arsenic into more mobile and toxic organic forms. So basically, arsenic is a very toxic compound. Other inorganic species, variety of other like cyanide, sulfate, chloride, fluoride, nitrite, nitrate, phosphate, so are there. So the eutrophication. Eutrophication means the phosphates, and those the it refers to the deteriorated condition of water body with excess algal growth. The phenomena involves the entry of plant nutrients, typically nitrates, phosphates. If plant nutrients are there in the pollutants, they go to the water bodies, and then they help the growth of the algal growth. Algae, weeds, they will grow rapidly. So then that will destroy completely the lake or pond where it goes and mixes. So that development of algae and weeds and unwanted plants is called eutrophication. Am I audible to all of you?
Yes, sir.
Next is ammonia is there, hydrogen sulfide is there. So then distribution of gases in water. So by Henry law, dissolved gases like oxygen for fish, carbon dioxide for photosynthetic algae are vital for survival of aquatic life. Gases like nitrogen are undesirable as it causes fish death. So nitrogen is undesirable, but other gases like oxygen and carbon dioxide, they are required. So the distribution of gases they can be found by using solubility of gases in water can be quantitatively estimated by Henry's law, which states that solubility of gas in liquid is proportional to partial pressure of the gas in contact with liquid. If the pressure increases, more and more oxygen or gaseous substance will dissolve in water liquid. Oxygen in water, that is called dissolved oxygen. So how is the actual how much amount of is the oxygen is the actually good for aquatic animals, which is about 7.03 milligram per liter at 35 degrees centigrade. So at normal temperature, 35-degree temperature, if you have 7.03 amount milligram per liter of oxygen is there in the water, that is called good dissolved oxygen. So next, carbon dioxide in water. Carbon dioxide in water gives you carbonic acid, which is a weak acid. Organic matter and dissolved humic substances in water. Organic matter is a complex mixture of organic compounds, including aliphatic and aromatic hydrocarbons, bearing functional groups such as amides, carboxyl, hydroxyl, and ketones, and others in smaller amount. On account of the interactions between the hydrological cycle and biosphere and geosphere, water usually contains organic matter. So, what is the organic matter? So basically, some organic matter is or humic substances, they are already naturally present. So that is called organic matter. So with this, I think we are done with the water chemistry. Now we will go to the next part, soil chemistry. Soil chemistry is about origin and nature of soil, soil composition, soil formation, soil chemistry properties, soil acidity, ion exchanges, cation exchanges capacity, macro and micronutrients in the soil, so then soil fertility. So these things are there in the soil chemistry. So what is the composition of soil? The soil is a meter deep layer with basic composition including mineral matter, organic matter, water and air along with microorganisms. Typically, soil is constituted of 45% inorganic or mineral matter, 5% organic matter, 25% water, 25% air. So composition: mineral to 45%, organic 5%, water 25%, air 25%. So that's the composition. Inorganic or mineral matter. What are the mineral inorganic components? So like clay, sleet, sand, gravel. So there are then also there are also primary minerals are there, secondary mineral. Primary mineral like silicate, quartz, feldspar, phosphates, apatite, oxides of iron, titanium, zirconium. Secondary minerals: aluminosilicates, kaolinite, Montgomery sulfates, gypsum, carbonates. So these are secondary, primary and secondary. Calcite, dolomite. Next, organic matter. Organic matter is about 5% constitute. So where they come from? They come from plant, animal residue, algae, fungi, nematodes, bacteria, nucleotides, amino sugars, cellulose, polysaccharides, and some organosulfur and organophosphorus compounds, lignin, fats, oil, waxes, and humus. So then water soluble organic carbon. The term water soluble organic carbon refers to the entire pool of organic carbon that is either dissolved in the interstitial pore water, or it served on the soil or sediment particles. Leaching of water soluble organic carbon becomes a source of dissolved organic carbon (DOC) in natural waters. DOC is operationally defined as the organic content that passes through a filter of size 0.45 micrometer and is the major form of carbon that gets transported with soil solution and in streams. So this is, so next, soil water. So water is there in the soil, as a 25% of water is there in the soil. Soil air. So there is also some kind of oxygen that is also occupied in the pores of the soil, porous soil particles. Soil formation can be is a process that is a complex process, and there are two soil formation process: weathering process and pedogenesis of soil development. Weathering: natural force like wind, running water, changes in temperature along with the action of living organisms lead to breakdown of rocks into fine, smaller particles that initiate the process of soil formation. So next is, it could be like the soil formation process could be also contains it primarily predominantly involves carbonation, hydration, dissolution, hydrolysis, oxidation processes, and reduction processes. Then weathering by biological agents also. In addition to these chemical processes, weathering also can be done by biological agents. Factors affecting soil formation: climatic factor, topological Prassi factor, biospheric factor, then soil profile. So what is the soil profile? You see, this is the soil profile: bedrock, C zone, B zone, E zone, A zone, O zone. O zone is the zone where the topmost portion of the soil where you grow the plants. Okay, O zone, uppermost horizon of the soil. Okay, A zone is horizon also called top soil. E horizon is a layer of illusion of clay and oxides of iron and aluminum by weathering. C zone is the soil zone that lacks organic matter and is largely composed of weathered mineral from parent rock. Beneath the C zone is the bedrock. So this is how your different stages or phases of your soil. Soil chemical properties. Soil has acidity. Okay, acid, either it is basic or acid. If it is acid, then less than pH less than 5, 6, 7, or it is neutral 7, basic less than greater than 7. So this is soil acidity. So ion exchange in soil and cation exchange capacity. Macro and micronutrients in soil. So what are the nutrients? Nutrients are essential for survival of plants in the soil. If we do not have enough amount of nutrients, the plants will not survive. So that's why there are two types of nutrient. Macronutrients means large amount of large nutrients that is required for the plants, and micronutrients means small nutrients required for the plants. So nitrogen is a macronutrient. Macro means it's lot of amount of nitrogen required for the survival of the plants. And then next is, what are the next? Phosphorus is also macronutrient. Lot of amount of phosphorus is required. Potassium is a macronutrient. Calcium, magnesium, sulfur, these are micro. Then macro, what is micronutrients? Like chlorine, iron, manganese, boron, copper, molybdenum, zincs. So they are recognized as elemental essential plant micronutrients. That means they are required only small amounts. Even if you don't have these, the plants can survive, but but their survival will be difficult. But the other, like macronutrients like sulfur, magnesium, nitrogen, so they phosphorus, they are definitely required by the plant in large amount. If they are not there in the soil, they will die. Soil fertility. Soil fertility is defined as the ability of soil to provide all the essential nutrients in utilizable form for uptake by plants. So fertile soil means all these essential plant essential your plant nutrients are there readily available. They can be easily taken up by plants. So that is called soil fertility. If it is not readily available, then that is not a fertile soil, or that cannot hold plants. That is. So with this we completed all these three processes, like your uh, atmospheric chemistry, and your soil chemistry and water chemistry. Anything you want to ask me? Anything you want to ask me?
Yes.
So basically, I can just tell you something more about this, maybe soil fertility. Soil fertility is defined as the ability of the soil to provide all essential nutrients in utilizable form from the uptake by plants in a balanced proportion. It is recognized as a combined effect of the three interacting components: physical, chemical, and biological characteristics of the soil. It is different from the soil productivity in the sense that fertility indicates the status of available plant nutrients in soil, whereas productivity is a result of various factors that affect the crop production, including fertility. So basically, fertility indicates that all the plant nutrients are available in the soil, whereas productivity is a result of various factors. Productivity means how much yield, whether you are getting a good yield from your crop or not. Whereas soil fertility means the amount of nutrient present is there or not, the required amount of nutrient present or not. So a fertile soil would contain all the macronutrients. Fertile soil means all the macronutrients like your phosphorus, nitrogen will be there. Okay, so potassium will be also there. A fertile soil also characterized by near neutral pH. So that means pH is almost same 7. If it is less than 7, it will be acidic. More than 7 is as basic. So that is also not required. So, and then presence of sufficient amount of soil organic matter that helps improve soil structure for optimal retention of moisture and nutrient elements. However, not all soils have optimum conditions for plant growth and all essential nutrients in adequate quantities. Soil fertility and crop production can thus be improved by utilizing fertilizers. So, if the soil doesn't have the required amount of fertility, we are adding fertilizers, we are using fertilizers like potash, like urea or phosphate fertilizers. So they provide plants the required nitrogen nutrients and your phosphorus nutrients and potassium nutrients. Common soil fertilizers contain nitrogen, phosphorus and potassium as major components, while magnesium, sulfate and few micronutrients may also be added. These fertilizers are designated as by numbers that represent the percentage composition of fertilizers. So, for example, a fertilizer numbered 6, 8, 12 is indicative of composition of 6% nitrogen, 8% phosphorus, and 12% of potash. Okay, fertilizers like manure usually correspond to zero point 0.5, 0.25 and zero point 0.5 composition and need to undergo biodegradation to release the nutrients in the form of nitrate, phosphates, and exchangeable potassium that can be readily assimilated by the plants. So this is about soil fertility, and then soil nutrients, as I told you. So this is nitrogen cycle. This is nitrogen cycle. Uh, Nitrogen is basically essential component of proteins and living matter and crop produced on nitrogen rich soil and therefore significantly richer in protein and more nutritious. An important source contributing the soil nitrogen content is atmospheric nitrogen fixation by leguminous plants like clover, soybean that contains a nitrogen fixing bacteria called rhizobium. Rhizobium is a nitrogen fixing bacteria. Those are in the roots of the plant, soybean and leguminous plants like clover, and present in the root of the nodules. Sustainable nitrogen content and soil fertility can be maintained by crop rotation between legumes and nitrogen containing plants. Okay, so the figure shows how uptake basically plants cannot take nitrogen cannot be uptaken by plant in the direct form. If it will be in nitrogen form, nitrate form, they are uptaken by the roots of the plant. Nitrates can be uptaken, ammonia cannot be uptaken. So there are some denitrification processes or nitrification processes. Ammonia is present in the soil, they are converted to nitrate via nitrification process. And also if nitrite is there, they are converted to nitrogen via denitrification process. So therefore denitrification is a process where available nitrates which can be directly uptaken by plants are converted to what? Nitrogenous or nitrogen gas. Okay, nitrogen monoxide, which is a very bad thing. Basically denitrification process doesn't help plants, but nitrification process helps plants, where ammonium ion or ammonia present in the soil, they are converted to nitrate, and this nitrate nitrogen in the nitrate form can be easily uptaken by the roots of the plants for their survival as a nitrogen source of nitrogen. Therefore nitrates are the source of nitrogen for the plants, not ammonia or nitrogen gas. Okay, understood? So, any questions you want to ask?
No, sir.
So, should I disconnect?
Okay, sir.
Or anything you want to ask? So another important thing is soil acidity. So soil acidity, if a soil is acidic, it cannot be used for cultivation. The acidity of soil is directly related to the soil mineralogy or organic content of the soil. Soil pH also has a direct effect on the solubility of metals, ions, and hence their availability and chelation capacity. Acidity of soil in the pH is usually measured in dilute 0.1 m solution of, of calcium chloride suspended in soil in water. So the acidic soil are generally rich in mineral ions. Some factors that contribute to lowering the soil pH are listed below. Production of organic acids, soil microorganisms, high organic matter content in the soil, loss of basic cations through plant harvest and leaching, addition of acids in the soil environment by atmospheric agents, greater uptake of cations than anions by plants, production of mineral acid in soil. Okay, so these are the ways in which soil pH can be lowered. And lower soil, if the soil pH is lower, then it contains lot of amount of what, plant nutrients. Okay, so I think if you have no more questions, should I stop now? Disconnect.
Okay, sir. Okay, sir.
Okay, thank you again. Tomorrow also, we have two more classes tomorrow and day after tomorrow. See you all tomorrow. Thank you all for
Okay, sir.
joining.
Okay, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.